Hey, how's everybody doing? Welcome back to the Math for Healthcare video lecture series. We're going to continue on with probability and Bayes' theorem. What I have up here, hopefully you remember from the last video, and I said I wanted to go over how we came up with this tree diagram, and I said we needed Bayes' theorem here. And actually, this is kind of when I missed something. I missed this 5% when I was talking last time. And so actually we don't really need Bayes' theorem, but it's a great stepping stone from regular conditional probability to Bayes' theorem, which we'll see in the next one. So if you recall here, we said it in a particular pain clinic, okay? So we're talking about our sample space is everyone at this pain clinic. And we got 10% of patients are prescribed narcotic painkillers. So that 10% is telling, and I'm going to say let K be the people that are prescribed painkillers and A be the person that's addicted, people that are addicted, okay, as far as events. So K here, we have that 10% thing that tells me that the probability of a person being prescribed painkillers is 0.1, right? That 10%. And of course, if not here, is going to be that 5%. 90%. What I'm saying is the probability of not being prescribed painkillers is, I'll put that point in there a little better. That got a little out of hand. I don't know how it got all the way over there. Is 0.9 or 90%. Now, okay, so that was good. We filled out a chart. We had that. And by the way, because it's this probability and it's not a conditional there that they're given, that should come first in our tree diagram, the first branches. Now next up we see I used, out of the people prescribed pain pills, 8% are addicted. Okay, so that's this 0.08, right? It's, what does that sentence say? Out of the people that are prescribed painkillers. So that's telling me the probability of being addicted given that we were prescribed painkillers. Right? And that is, of course, on this branch here, we got, okay, let's see, we know, what do we know? We know we were prescribed painkillers. So we're standing here, right, out of all the people that are over in K, prescribed painkillers, 8% of those are addicts. That gives me this probability of A given K, or the probability of being an addict given you were prescribed painkillers is 0.08. Okay? And that automatically, the way we draw tree diagrams, makes the probability of not being addicted given being prescribed painkillers is 0.92, which of course we related. Now notice we had these question marks. We didn't know what these other branches are, which, let me write those down in symbols what they are. Let's get this. All right. This should be the probability of being an addict given you were not prescribed painkillers, and the probability you're an addict given, or you were not an addict given you were not prescribed painkillers. That's what would go in those. And now we don't have either of these. What was this 5%? That's the last thing we need to read. Well, that 5% is telling us that, let's see, 5% of the clinic's patients are addicted to narcotics. Now, and that's what we mean. That means that they're in A. So that's telling me the probability of A is 5%. Now, convince yourself that's correct. 5% of the clinic's patients, not necessarily the people that have been prescribed painkillers, just the So it's not a conditional probability. Notice that doesn't give us either of these branches. Okay, that's okay. What are we being asked for? That's the next thing we want to double check here. If a patient is an addict, what is the probability that they'll be prescribed pain pills? Okay, so that's the probability that someone is prescribed painkillers given that they are an addict. Now, we're not given that. We have to find it, okay? So, let's look at this. Here, we're not quite using Bayes. We would use Bayes if we had those two red starred branches. But look what we do have. Since we have the probability of A, let's go back to our conditional probability formula. It tells us the probability of K given A. So the probability you are prescribed painkillers given that you're an addict, that is, hopefully you know this, the intersection over the probability of the intersection over the probability of A. It's our sample space shrinking, right? That's what's happening. That's why it's the probability of A down there. And notice, okay, we don't quite have those numbers. We have the probability of A. How about the intersection? What is that intersection? That, pick a different color here. That intersection is which path? I like to remember we think of the intersections as path. It's okay. K intersect A. I'm down that path. And I know how to find that intersection using our product rule, even though they're not independent. And we're going to write down that formula. That's going to be probability of K. This is just basically following down that black path there times the probability of A given K, which we have. And then, of course, probability of A carries on. So I'm going to do some calculations here. You can see that upper one a little bit better. We know, all right, probability of A is 0.05. Probability of K is 0.1 times the probability of A given K is the 0.08. We'll do that over here. Finally, well, we'll plug it in. 0.1 times 0.08 divided by 0.05. Looks like 0.16. All right. So here, if a patient is an addict, the probability that they will be prescribed pain pills is 16%. All right. And a lot of this is seeing the words and seeing as distinguishing between conditional probabilities and non. Right? Again, overall, the 5% of the clinic's patient, that was not a conditional probability. So go ahead and review those. Make sure you understand those sentences. And now we'll move on. And this is the basis of, well, what is the basis of Bayes' theorem, which we'll need in the next problem? Well, let's take a look. Let's just say we had two events in a tree diagram. All right. A, not A. These are just general events. I'm not going to even name what they are. We'll give some meaning to them in the next example. Oop, a little high. All right. So, and let's just write in our general tree diagram. We got probability of A complement, probability of B given A, probability of B complement given A. Here we got the probability of B given A complement. And lastly, the probability of B complement given A complement. All right? And we have to search and see which ones of those things we have. In order to fill this out, notice these conditional probabilities, we have to be able to analytically find them. They have to be given to us in a sense. So here we are. And think about what our question was. Let's say we knew the probability of B given A and all these conditional probabilities there. But that last question was kind of like asking us, okay, find the last question was saying find the probability of A given B. Okay. Right? Smaller, so I got some room to work here. Oh. Okay. Now we know the formula for this. We just used it on the last one. This is the probability of A intersect B over what? The probability of B. Now notice we don't know in that last problem we didn't know the probability of in the last problem we knew the probability of what is taking the B here. But what if we don't? Well, how does that probability of B relate to the tree diagram? Well, we could think about it as all paths to B, right? I could go through A, and I could go through A complement to get to B. Those are the two paths to B. All right, so maybe let's write that down here. This is probability of A intersect B. Let me get A intersect B divided by, do it in green to match that path. What's the probability of one of those two paths? Here we use it. We could either go through to B through A, so that's A intersect B, plus the probability of, well, it's the other path, it's through A complement B. All right. Now we have a bunch of intersections. And we could finally do our last formula, which is generally the form of Bayes' theorem, and notice, what's this? Let me see this numerator here. I don't want to do it. This numerator here is the probability of that intersection. We could think of that as this yellow path, right? That part of it. So now, well, we could use our definitions. What do we know? The probability of A intersect B equals the probability of A times the probability of B given A. And notice we have that. And we divide by, well, certainly we still have that intersection. Plus, what's the probability of the intersection of A complement and B? It's the probability of A complement times the probability of B given A complement. All right, and yes, is that fairly long formula? It is. That's why I tend to think of it in the tree diagram sense. What is this? You take the path that you want, so here the yellow path, and divide by all paths that go to B. Okay? And I guess what I would say is those are the green. And of course, the path you want and all paths to B should overlap. In other words, you should see that yellow term again down here, right? Your yellow path, because they go over the same spot. All right, so that's the full formula. Again, I think of it as paths, and instead of formulas, I think it's a nice way to gain some understanding on that. So let's look at our next problem. If, or so, sorry, 1% of people have a certain genetic effect, or genetic defect. 90% of tests for the gene detect the defect, true positives we call those, and 9.6% of the tests are false positives. If a person gets a positive result, what is the probability they actually have the genetic defect? All right, so here, the first thing is, just like in the linear and the exponential section, we want to define what we're using. So I would start with defining our sets of interest, which in here I would probably call DB set of people with genetic defect. And I'll just use positive sign for set of people with positive test. All right. And by the way, for the complement of positive, I'm just going to use negative in this case with tests. All right. So using those, I'd try and build your tree diagram, all right, on your own, and then hit pause and then come back in and let me know, or follow along where you may have missed anything. But let's see here. What are these numbers? We have to pick them out carefully. Now, we got 1% of people have a certain genetic defect. All right, so right away that's saying the probability of D equals 0.01. 90% of tests for the gene detect the defect, so true positives. What is that? That's a conditional probability. The probability of testing positive given you have the genetic defect, and that's saying that's 0.9. And then let's see here. What's the other 9.6%? What is that saying? That's a false positive. So that means probability of getting a positive test given you do not have that genetic disorder, and that is equal to 0.096. All right. So if you had trouble doing the tree diagram before, maybe this will help you. Maybe hit pause again and try this out. All right. And I'm going to continue on now. So let's draw our tree diagram. I'm going to give myself some space here. See if I can't make it happen with that. Let's, right about there. Okay. So what does our tree diagram look like? You either have the disease or the defect or you do not. Then you either test positive or you do not. Test positive or you do not. All right. Now let's put in our probabilities. So, see, we're given the probability of D is 0.01. That's the probability I walk along that path. Probability that a person has that certain genetic defect, so that the probability of D complement is going to be 0.99, right? It's the complement, 1 minus that. Then over here, what are we looking for? The probability that we test positive given we have the defect. Make sure you understand how you're reading that in the chart. And that's, of course, right here. This is our 0.9, so the other branch has to be a 0.1. And then notice this last thing, probability of positive test given we do not have the defect or a false positive, that's 0.096. And then 1 minus 0.096 is going to be point. 904. All right. Now, there's our tree diagram. All right. What do we ask? What is the probability that they actually have if a person gets a positive test result, what is the probability that they actually have the genetic defect? All right. So we're being asked if they have a positive test result. So what's the probability that they have the defect given that we test positive, right? Now notice this is not the same as the probability that we test positive given we have the disease. Those are two different things. That's one of the big things to see. These are not commutative. All right. And we know this equals the probability of their intersection over the probability of the intersection plus the probability all paths to a positive. So not having the disease intersect positive. Good. Now, how do we calculate those? Again, I think about the numerator and denominator more in paths. So the green path is our numerator. Okay, what is it? We have the disease and we test positive. That's the numerator. What's the denominator? The smaller denominator is, I'll do those paths in yellow. Those are all paths to positive. All right, so there we get that. Now we plug our numbers in. All right. I'm going to move us up a little bit. I know we're going to lose a little bit of the problem. I think there will be good. And we'll say that this is equal to, it's going to be, what's the green path or the probability, or in other words, say probability of the intersection of D intersect plus is going to be 0.01 times 0.9. All right. Divided by, now we want the yellow paths. 0.01 times 0.9 plus what's our other one? The other path is 0.99 times 0.096. All right. And we end up with, plug that in, 0.01 times 0.9 divided by, notice I need to do parentheses when I divide now. 0.01 times 0.9 plus 0.99 times 0.096. Okay. 0.01 times 0.9, 0.9, 0.99. And it looks like you only have a 8.5% about percent. 0.87, about 8.7% chance. So this has to do with the rarity of the disease. And it's something to think about when you're given tests of false positive rates and accuracy rates for a test. All those things are great, but it really depends on how scarce the disease is. Hopefully, I want you to think about it. And if you wanted, I would think about this, but if it really is bothering you, it doesn't seem to make sense, think about it as, okay, I have 100 people. That means that if I had 100 people, right, one of them would go to D. One of them would walk the green path to D, and then let's say it's 0.9 of that, so let's just round up and say that one would also get tested positive. But 99 people would be walking to without the disease, and then about 10% of those, so about 10 people would walk the rest to the positive, would get a positive test result, and you would have 10 people there compared to one person up on the upper branch. Let's try it out, try and sort that out. I'm a little over time here, so I'll post another video on using Bayes' theorem, and I'll also post an older video I did on thinking about antibody testing for COVID early on and back in 2020. But I think it's a worthwhile video for you to watch. All right, try a few problems on your own and let me know if you have any questions.